Welcome class to chapter 10, where I'm going to review the related paired samples t-test. And remember, you're going to use the related samples or paired samples t-test with a within subject design and a matched design. What is a within subjects design? Basically, think about it as the same person is going to get different treatments, for example. And the pre-test, post-test is a famous one where you have a before and you have an after. Let's see what I have up here. Why did I even write it, right? Data is collected from a single sample in two environments or conditions. One common within subjects design is the pre-test. Post-test, a type of research design where behavior is measured both before and after a treatment condition is implemented. And of course, you're going to compare, right, the after scores to the before scores. And hopefully, like if you're predicting, improvement, you're going to have an increased positive score, right, for those. A matched design is a different type of design where you will use the paired samples t-test. And a matched design is a between subjects experiment. Now, within subjects, same person, right? Between subjects, you're going to have different people going into different groups, and you're going to be comparing those groups. Not the same person going in to do two different treatments, but different people going into the different groups. A matched design is a between subject experiment that involves a set of participants matched on a specific characteristic. For example, each member of the set is randomly assigned to a different level of the independent variable or not. They give in the book the example where they're not necessarily randomly assigned to different groups. But they're really, the key with the match design is that they're matching each participant on some type of pre-existing variable that they think will negatively affect the study. As I say right here, they're trying to account for pre-existing variables as possible confounds. For example, in the book that they give, they're matching each student up in each section with the past performance on tests. So they're comparing each student with online quizzes versus no online quizzes, and they're basically matching them. And the way to do that, or the reason why they do that, they often do it with IQ. If you're comparing a IQ, something that might improve IQ, is you're trying to pair them up, and so that one group is not unequal than the other. You're trying to match them up on some characteristic that you think is going to be a confound. What if one group is, much smarter than the other group, and then you happen to give them the online quizzes? And it's not the online quizzes that help them, but the fact that they had this pre-existing variable that they were smarter than the other group. So the thing with the match design and why you do the paired samples t-test with it, which would be a good statistic for it, or the reason, or not why, but it is a good statistic for it. The idea is that you're trying to essentially match them up on a variable that might be a confound. And you, again, use the paired samples t-test for both within subjects design and a matched design. Okay, so even though it's a between subjects design, it's a matched design. And so they're dependent in some way, these scores. And that's why you use the paired samples t-test, also called a dependent samples t-test. In other literature, the steps of the hypothesis test are very similar to the one sample t-test, except we will use the mean of the difference score, D with a line over it. Become familiar with that new term, right? New statistical symbol, rather. Then the mean of the raw scores. So notice this equation where you have the previous one sample t-test, where you have the mean of the raw scores minus the population over the standard error. And in this case, the paired samples t-test, you're going to have the mean of the difference score minus the population, which most of the time is 0, over the estimated standard error for the difference score. And that's the standard deviation of the difference score divided by the square root of n. So instead of the standard deviation of the sample, you're going to use a standard deviation of the difference score divided by the square root of n. So they're basically very similar equations, right? But we're using the difference score, and we're going to be able to see adjusted by error if that gives us a positive t value, right? Okay, so what are the different scores and how to figure them out? They're really not too difficult to figure out. In the example they gave, can fortune tellers do better in their fortune telling environment, right, versus the lab? Does the lab, being in that like artificial lights and everything, kind of throw them off? You know, do they need their dark lighting and incense and crystal ball or whatever that they use? You'd ask them and tell them to create the environment right there. And then, so you simply subtract the score for each condition from the other condition. For example, okay, are they doing better in their fortune-telling environment? So we're going to subtract their scores from the lab scores. And you'll need to calculate the different score for each subject or pair. And in this example, it's going to be a subject, right? And the fortune-telling versus the lab condition. And because it's a within subjects design, calculate the mean of the different scores, D with a line over it, there's the symbol there, by adding up all the different scores and dividing by the total number of subjects in a within subjects design or pairs in a matched design. An example I give here with the fortune-telling environment versus the lab environment, let's say that you have 5 participants, just to make it simple here. And so in the fortune-telling environment, this participant earned 30, and then in the lab, not so good, 25, 30, 25, 30, 25, another person 30, 25, another person 30, 25. So you have 5 different people here. And so their different score is 5, 5, 5, 5, and 5. Add them up all together, you get 25. Divide by the total number, 5, and the mean of the different score is with the D with the line over it, right, is going to equal 5 in this example. And so let's take a look at how to calculate a paired samples t-test. So again, we're going to step 1, state our hypothesis, right? And in this example, the alternative hypothesis is in the population, the mean difference score should be greater than 0, right? That we expect when we subtract that fortune-telling environment from the the lab environment, that we're going to have a positive score greater than 0. And the null hypothesis in the population, the mean difference score should be less than or equal to 0, right? And we compare the sample mean to 0 because if there's no effect of condition on the dependent variable, then we expect no difference between the scores from these conditions in the distribution of sample means, right? If they are not going to improve in their fortune-telling environment, right? If it's just going to be same, right? And that's the null hypothesis, right? No difference in environment, right? Then the means should equal 0. And alternatively, if there is an effect, then the difference between the two groups should be greater than 0, right? We should have, like in the past example that I just gave, where it's ostensibly was an effect. Let me get back there. Right here, it was 5, right? And so the null hypothesis would be that they would just get 25, 25 each time. Same, no difference, right? In terms of the environment. So alternative hypothesis, higher accuracy for the fortune-telling room than in the lab room. Null hypothesis, worse or equal accuracy for the fortune-telling room than in the lab room. Of course, the book talks about that we must pay attention to the order in which we do the subtraction. And if you're predicting a positive difference score, then you want to put the fortune-telling first, right? And fortune-telling scores first. That way, you're going to be subtracting those 35 scores from the 30, right here, and it's going to give you a positive difference score. If you flipped them around, it would give you a negative score. So you just have to pay attention. The book talks about that. And it's just obvious, right, that you'd want to put the one that you're predicting as better scores as the first one if you're going to predict positive scores. Step 2, set your decision criterion. As is typical for behavior research, we're going to set our alpha level at 0.05. And step 3, we're going to collect the sample data. In this example, they collected sample data from 50 psychics, and they participated in the prediction tasks. Don't forget, in both rooms. So that's a within subjects design. It's a one-tailed because we're expecting the results to be positive for the dark room, the psychic room. And this breaks down that big flow chart. I don't think I put the big flow chart in here, but you know which one I'm talking about. And in terms of, okay, we're comparing means. How many sample means? 2 we're comparing. Is it a between subjects or within subjects? In this case, it's a within subjects. So we're using the paired samples t-test. If it was a between subjects and a matched sample, we would again use the paired samples t-test. Step 4 is to calculate the statistics. So we have the mean difference score here in the example that they give. Is the mean difference score was 1.0, and the standard deviation of the difference score is 2.9. So these are the, and then n equals 50. So remember, before you start doing your tests, because remember, doing these by hand is just a simple matter of plugging in the right values, having your right values in front of you, right? Kind of like, what do they call that? Mise en place. I probably murdered the French of it, but having all of your materials in front of you, very easy to cook, right? If you have it all chopped up. And in this case, you want to have what you need for the equation, the paired samples t-test equation. And so you have the mean of the difference score, and then the standard deviation of the difference score, 2.9, and then n equals 50. What you're going to first do is figure out your estimated standard error for the paired samples t-test. And so the estimated standard error for the paired samples t-test for the difference scores is S with a sub D with a line over it. And then you're going to take the standard deviation of the difference score over the square root of n. So we just plug in 2.9 right there, and we plug in 50 right here. Okay, and that gives us around 7 something, right? Because sometimes 7 is 49. 7 and a little bit. And so essentially, what is that? That's about 0.41. And that looks right in terms of my calculation, right? That makes sense, yeah. And then now we're going to do the t-tests. And so we're going to take a look at our calculated t-value, right? And then compare it in the charts, just like we did for our one sample t-test. And so t equals, remember the mean of the difference score right here is 1. And then remember, we subtract it from 0 because we expect there to be no difference between the two conditions as the null hypothesis, right? And if there is a difference, then it's going to show right here, right? Okay. And then we also have the correction factor, right, where we have our estimated standard error underneath it that corrects for the chance of that we're making an error drawing from the samples from the population. And when we do that calculation, it gives us a t-value, right, of 2.44. So again, 1 is here, minus 0, you do that if you're predicting no difference, right, over 0.41 that we already figured out, which was our estimated standard error. Look it over a couple times until it sinks in, right? So now we have our t-critical value of 2.44. And we have to figure out, remember, our degrees of freedom before we go to the table and look that up on the chart. And I already did in previous videos how to look up the t score, your t-critical value, to figure out if you can reject the null hypothesis and say, whoa, these are spectacular results, these are amazing, these are make our null hypothesis look ridiculous, right? So you figure out your degrees of freedom, df equals n minus 1. N is 50, minus 1 is 49. So we're going to look that up on the table, 49. And the critical t-value for a one-tailed test, remember this is a one-tailed test, right, is the t-critical value of 1.677. So is 2.44 bigger than 1.677? Yes, of course it is. Compare the sample t-score of 2.4 with a t-critical value of 1.677. The sample t-score falls in the critical region of the distribution, right? And our study provides evidence that the room has an effect on the psychics' accuracy rates. It doesn't mean that the psychics are better than chance. In this case, they were, right? If I gave you, well, in the 5, we equaled it the 5 different scores they were, but in this example, it doesn't mean that they are better than chance. But it does say that the psychics do better at prediction in their psychic conducive environment. And of course, there are 2 test assumptions that we've already reviewed before, but you want to make sure that you have in order to do a paired samples t-test. And they are: the population of different scores must be a normal distribution. This assumption is necessary in order to ensure that the values in the t-table are accurate, right, that you're comparing to. And when the sample size is 30 or larger, then the sample that was selected at random from the and sample is selected from random from the population. Violating this assumption does not change the critical t-values enough to change the outcome of the hypothesis test, because the distribution will be normal as you get higher up above 30. The scores from different, the assumption number 2, similar to what we talked about with the one sample t-test, the scores from different participants or pairs of participants must be independent. This means that across the subjects, or across the pairs of subjects for match design, the scores cannot depend on the scores of other participants or pairs. And they give the example before, a good example, that you want to have soundproof rooms, for example, that you don't want other psychics to hear each other making predictions, so that the scores don't influence each other. You want to make sure that the scores are independent of each other. And that is it for paired samples t-tests. I hope it was helpful.